Okay, so talking about the post operation, we can introduce some terms as your common knowledge. So the type, the XY axis is time, Y axis is power. So it go on and off. So this is the dash curve is the EDO on and off curve. But it usually needs some time to turn on, some time to really turn off. And then the region with the higher output power, we can call it the TR. And while it's repeating itself, you have a time period. So you can evaluate first the time T on, we can call it pulse width. Since we're sending the signal frequently. And then we can also change the repetition rate from its period. It's like 1 divided by TP. 1 second divided by TP second. If it is only 1 microsecond long, that means it's gonna repeat the circle 1 million times per second. So the repetition rate will be 1 megahertz. Yeah, so you will something like the repetition rate from the spec of laser. There's also some common term called the duty cycle while you're reading the spec of a solid state laser. That means how many of time is occupied in its on state. So that will be T on divided by TP, that times 100%. So you might see the DC as 0.1% or something. Yeah, because you want to get a high intensity at a specific time to get a stronger excitation, but you don't want to burn your device. So it only give a very short term to on and let it cool for the rest of probably 99% times to let it cool down. So the lifetime of your laser will be longer. And sometimes you will also read its value as some peak power and the average power. It usually only give you average power. Since average power is pretty difficult to measure the power at a specific smaller time, you usually need some time for integration. So the measurable one is usually average power because you need a second tool to really check what the power is. So the average power, but what really matters is the peak power because that give you the most carrier density at a specific time. So the relation will be the P divided by P max surely will be T on divided by TP. Okay, so you can evaluate your P max. Usually P max is not measured. It can be only evaluated. It will be the average peak power, average power measured by a surge detector. Divided by that is the duty cycle in your spec of lasers. Okay, then there's another term called the continuous wave. This is also pretty common in the paper relevant to lasers. Continuous wave is usually abbreviated CW. CW operation. That means your duty cycle is 100%. Yeah, so you can also get the duty cycle 100% is also direct current, so it's all DC. Alright. Let me drink some water. Okay, yeah. How many pages left? Okay, 3 more. Okay. And the thermal effect, 热的效应 is also very important for the real laser diode. This is a simplified circuit for a laser diode. You turn your injector in, and there's a shear resistance. Then attached with a diode, and such diode will emit light. So usually this part is only for explaining. We usually only have this one on your circuit. And after turning I0, you get some output. So the total power insert this device will be I0 squared times S, the joule heat, plus the I times the VD. VD is the diode voltage. Okay. And the sum of the energy will be transferred as the photon energy. So the photon energy doesn't contribute heat, but the rest of them will. So the power for dissipation will be I0 squared Is times IVD minus the output power you measure. And such heat will, such energy will heat up your device, and that will make your device energy, device temperature different from your environmental temperature, or we can call it the sink, the heat reservoir. Delta T is equal to T device, the device energy, minus the environmental energy, and it will be proportional to PD. If you have more power to dissipate, surely your device will have a higher temperature. And the linear relationship is linked with a term called ZT. ZT is the thermal impedance. If ZT is high, that means the power cannot be transferred from your device to your sink. So it's impedance, just like a resistance. In this case, the temperature will only heat up your device, so you will have a higher device temperature. Okay, so there's the result. So how do we evaluate the DTU? So there's the three common cases of your device structure. One is the device down, because your device is growing on your substrate, but you will make your device 180% directly attached on your reservoir， 就直接把你的元件直接放在一个 reservoir 上面。So this is the best way to transfer heat, and the distance between your device and the heat reservoir is h, and A is the area of your device. Okay, so this is one package size. Second package is common edge emitting laser. The substrate is thick, and the whole substrate is attached to another heat reservoir. So you have a pretty high edge, and the W is the reach width. So your current is injecting along this line, and this is your heat source or the power source for dissipation. So your power need to dissipate from this end to a relatively long term to your reservoir. So this is the case of edge emitting laser. And the third one is the case of diesel. Diesel, the power source is relatively small. It's usually a small circle with diameter S. Okay, so this book is very friendly. Tell you in these three cases how do you calculate your DT. So you will just choose your recognize your device structure and choose the right model. Then calculate relevant DT. We will have some example for you later. Okay. So what's the problem with the temperature? We know that if your heat dissipation scheme is 2, that means your package is not bad. It's bad. Or the resistance is high, you have a higher PD. Then you will get a higher power in your device. What's the problem? The major change is because it's a Fermi-Dirac distribution. When the temperature increases, the DOS will further. If you see the density of state, T is in the powers of 1.5. So when the temperature increases, the effective density of state will increase. Then, if you want to reach the same Fermi level separation, you need to inject more carriers. But let's put another side. If the injection current level is the same, but the temperature increase, that means your Fermi level separation will decrease. With the smaller Fermi level separation, the gain also reduces. So it will be more difficult to reach threshold carrier condition. So what will happen? The threshold gain also increases. No, the threshold current also increases. Threshold gain is the same, but the threshold current, the threshold carrier density and the threshold current all increase. Okay. So in the term of the ITH, you will see that it will lower your IQE due to a higher order recombination. Also increase the NTR because your Fermi level separation decrease. And also, probably also you have a more higher internal load because your free carrier absorption will be more assisted by the lattice vibration. So alpha will also have some influence on that. But anyway, it all tells you when the temperature increase, your threshold current density will definitely increase. And we see the differential efficiency. Alpha and probably no big change. But the fact, because the current increase, the electrical confinement design will be weak, since you have lots of electrons at a higher energy tail. So the injection efficiency also weaken. Zeta I becomes smaller. Alpha increase, so it will make your lacing with the low smaller slope. Okay, so let's consider the IV curve, probably already next page. If you have a pulse laser under room temperature, because it's under short pulse, so the device itself don't contribute much. Probably you have a PI curve like this. But under high temperature, first we know that ITH will increase. Second, the laser will also have a smaller slope. So from any perspective, it becomes a worse laser, and it degrades pretty fast with temperature. So we usually model that the ITH and the zeta D as a function of temperature. And we call ITH will increase exponentially with T, and model it with a parameter called T naught. If you have a higher T naught, that means your device is more resistant to a higher temperature. Okay. And you see that when T is higher, your threshold current density will be higher. And for differential efficiency, because it will reduce. So it also modeled the exponential term, where you have a minus term here. Also modeled by another parameter called the T zeta. If the T zeta is high, that also means your slope is more resistant to the temperature. Okay. So since we don't know what the I0 and the zeta T0 is, we need a reference since it is only a fitting parameter. For example, you might have T you might have ITH on the T is equal to 300K with a known value that's called I300. And we can model that ITH, it should be I0 exponential T over T9. And the ITH T is equal to 400, for example, 400K. This will be I0 as exponential T400 over T9. And you can divide each term to eliminate the unknown parameter. So I T will be I TH is reference times exponential T9 under T minus REF. I TH REF exponential plus a delta T over T9. Okay, so this is the equation. What it comes from here. Similarly, we applied it to the slope efficiency. Okay, so the reference probably is the pulse condition. That means no heat energy, no heat influence with exponential minus delta T divided by zeta. And finally, this is the term with zeta T and the ITH. So under real application, you have 5 equations coupled to each other. So we will practice how to solve this iteratively. It's actually not that difficult. Why? 2Wx is 500. And the subtraffic after polish is around 200 micron. It's all pretty close to real value. Okay, when the laser is operated on very short pulse, that means we can basically neglect the heating by the device itself. Alright, and but the environment is 300K. We found that the ITH is 50 milliamp, and differential efficiency delta D is 0.4. Okay, not too bad. According to the IV curve, we can see that its shear resistance is about 50 ohm. Alright, and now we know the heat conductivity. To see, okay, this term is very difficult to write and pronounce. To see, 不是洗 okay, to see is 0.08. Notice it is unit watt per centimeter per Kelvin. First, calculate is thermal impedance. You want to know ZT first for calculation. Second, if this device is operated on a continuous way, so now with the heating issue, what is new threshold current condition? Third, what's the output power under 100 milliamp under threshold condition? Okay. So the first example, we just put the number in. For the laser, dt is too long for h divided by w, I divided by pi cl. So we just put the old number in. The h is 200 micron, w is 5 micron, and since we need to be careful, the c here is in the volume of the centimeter, but we know the length is the 600 micron. So you need to unify the relevant unit to get a reasonable number. Yeah, because since sometimes it's in centimeters squared, sometimes it's micron. Yeah, be careful to unify that to make a reasonable value. So the dt here is around 40 Kelvin per watt. Okay, so first one is done. It's simple, just try to put the number in. So the tricky part is, what's the ITH? We only know the ITH should be some value larger than 50. Since it's heating, but I don't know what it is. So let's get a first guess. Let's guess if the ITH should be 55 MA. Okay, so at I is equal to ITH, the P0 is 0 since I is equal to ITH. And the power for dissipation will be 55 milliamp times its shear resistance plus IVD. The I is 50 milliamp, and the VD is the ideal diode voltage. The ideal diode, what's the ideal diode? Oh, that means the electrical energy is transformed into the photon energy perfectly. So for a 1.55 micron, the photon energy 1240 divided by 1. And this is ideal diode energy. Okay, so this is VD plus 0.05, and the output power is 0, so minus 0. Okay, so the power for dissipation is 0.23 watt. Then we have the delta T will be 8.9 Kelvin, since we tie two numbers together. And the ITH, then we have the delta T here, and then we know the reference ITH is 50. And delta T is 8.5. And the T naught is given for 50 Kelvin. Okay, so the ITH will be 59.8, which is a little bit higher than your guessing. So then we can make a second guess. Alright, so if we make a second guess that the ITH to be 62 milliamp, and repeat this. Okay, to here we found the ITH to be 62.4. Still a little bit larger, but it's already less than 1%. So probably you can also try 6.5 or something. Yeah, if you can try to approach it very clearly, but it is already pretty good enough. So I will take the CW will be 6.2 milliamp. So in your homework, you have to tell me what your criterion is, because you need to find that. You can say that after 2 iterations, I find the error is already less than 1 milliamp. Okay, I will take that. Or you can say that the difference is already less than 1%. I will also take that. But if you give you no preference and stop somewhere, probably not good enough. Okay, you need to, it's just like while you're doing calculation, you always need a criteria for convergence. You're not going to do that with an infinitely small. That will be impractical. Anyway, for this case, we found the threshold current density increased from 50 to 6.2 milliamp with acceptable precision. Okay, so what is the output power under I is equal to 100 milliamp. Okay, so now here we do the same thing, but we build an Excel table. First, the iteration 0th, that means we need to do a first guess. It's actually, if you do a guess closer to real value, you will need a less iteration to do that. But if it's too far away, actually you will still eventually to approach some numerical value, but that will be not smart enough. So we do a smart guess. So let's assume the first IPH should be 62, but actually it should be higher. Alright, so now we have I is 100 and the IPH is 62. We can calculate the P0 here. And we can also start with some zeta t. Probably you can use the value I give you at the beginning with no thermal effect. But no matter what, it will eventually converge. Okay, so we have P0. We can calculate, and we give you a current. We give you the shear resistance. We can calculate the power for dissipation. Then we have power for dissipation. We can calculate the delta T. Because this is the constant that doesn't change. Okay, we have delta T. Then we have delta T. We have the new IPH. And the new IPH and the new zeta. Okay, so we have the new IPH and new zeta. We can feed it back for the first equation. So now from the first row, we can link the first IPH to the column here, and the zeta D to the column here. You will automatically generate a number as your new P0. Okay, then you also can put the zeta T as the P0 from the entity above it. So we can link the relation between these two. Similarly, for the delta T, we have this delta T. With delta T, you have new IPH and the new zeta. And you can scroll this entity one step forward. And it automatically feeds these two numbers to your new P0. And do the same, because this entity will eat the value from its top. Again. Okay, so you see, the rest of them is already automatic. You can also do that with MATLAB if you think they will be easier for you. But I only have Excel, so I prefer to use Excel. You see the value after the second round, third round, fourth round, fifth round. From the third round and the fourth round, you see these two is already identical. So this value converge. So the real output power is actually around 4.5 milliwatt. Since the P0 is calculated with watt, so this is 4.5 milliwatt. Alright, so under real temperature, under continuous wave, let's consider if this is the pulse operation, it's very short pulse. no heating, so it should be a direct line. At a higher temperature or under CW, first the ITH will shift to a new ITH. Well, you increasing your current because there's some heat for dissipation. So the ITH might increase a little bit further, and the zeta D will decrease a little bit further. But it's under a specific I. Then the intersection of this ideal line, the new convergent line with such current is the point you get. It's only true for this point. Because while you're increasing more current, the zeta, the threshold current, and the slope will change again. So it is only true for a new line at such point. So we do that with higher current, you get, for example, this one, you get another point. Even higher, another point. When the injection current is really is high to some level, if the output power doesn't increase anymore, it will overload. Since the ITH increases so much and the slope also decreased a lot, so it reached its maximum point, then goes down. So you will get a real Li curve due to the device self-heating. Alright. So this is the thermal rollover is usually serious for VSO because the package, the power, the area of the key source is small. So the power density for dissipation is high and the ZT is high. So we usually see a pretty and significant thermal rollover for VSO rather than ELS. For emitting laser, surely there will be the thermal effect, but since its space is large, so the dissipation is faster, and the power usually encounter another failure mechanism before the rollover. So usually we don't discuss this kind of rollover for ELS. It's usually most encountered in VSO.